Today we will cover sections 8.1 and 8.2. First, we will start with section 8.1, which deals with geometric means. So we have a proportion right here, which is A is to X as X is to B. And it is important to realize that X is the mean and A and B are the extremes. Like in the proportion we have here, when the means of a proportion are the same number, that number is known as the geometric mean of the extremes. So here, X would be the geometric mean of A and B. To find the geometric mean between two numbers, you take the positive square root of their product. Let us find the geometric mean of A and B. So as we said before, we're just going to take the positive square root of the products. So we have AB equals X squared. We're going to take the square root of both sides, and we will end up with radical AB equals X. From the work we just did, we can come to the conclusion that for any two positive numbers, A and B, the geometric mean of A and B is the positive number X. Let us try another example. So let us find the geometric mean of 32 and 8. So we know that X equals square root of AB. So then we're just going to plug 32 and 8 for A and B. So we get X equals radical 32 times 8. And we'll get X equals radical 256. And the square root of 256 is 16. So 16 is the geometric mean of 32 and 8. Let us try another example. We have find the geometric mean of 9 and 4. So X equals square root of 9 times 4. X equals square root of 36. X equals 6. So 6 is the geometric mean of 9 and 4. We will also have problems that do not contain a perfect square, so you need to find factors that are a perfect square. In order to complete these problems, we have to know how to multiply radicals. Here are some rules. First, multiply what's outside the radical together. Then, multiply what is inside the radical together. Simplify the expression by finding factors that are perfect squares. Let us try some examples. So we have radical 6 times radical 5. And this will give us radical 30. Now 30 has no factors that are perfect squares, so radical 30 is the simplified answer. If we have radical 8 times radical 4, you multiply them together, you get radical 32. 16 is a perfect square and a factor of 32. So we could split radical 32 into radical 16 times radical 2. And the square root of 16 is 4, so the answer will be 4 radical 2. We have 2 radical 3 times 4 radical 6. Our first step is to multiply the terms outside the radical. We will multiply 2 and 4 and get 8. Then we multiply the radicals and end up with radical 18. So we have 8 radical 18. And then we notice that 9 is a factor and a square root of 18. So we split it up to 8 times radical 9 times radical 2. And we end up with 8 times 3, because we're taking the square root of 9, times radical 2. We multiply what is outside the radical, and we get 24 radical 2. Now that we know how to multiply radicals, let us apply what we learned and try some more complicated problems with finding the geometric mean. So let's find the geometric mean of 11 and 7. So we plug it in and we get x equals square root of 11 times 7. We get x equals square root of 77. 77 does not have any factors that are perfect squares, so radical 77 is your answer. Let us try 2 and 22. So we get x equals square root of 2 times 22. X equals square root of 44. And we could split 44 up into radical 4 times radical 11, because 4 is a perfect square. And we will end up with x equals 2 radical 11. Let us do one more. Let us find the geometric means of 10 and 20. So we get x equals square root of 10 times 20. X equals square root of 200. And we could split that up into radical 100 times radical 2. And the square root of 100 is 10, so we get 10 radical 2. We can apply the geometric mean to certain theorems. So we have the geometric mean altitude theorem. This states that the length of the altitude to the hypotenuse of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse. You can see this diagram right here, and h, which is the hypotenuse, equals the geometric mean of xy. We also have the geometric mean leg theorem. This states that the altitude of the hypotenuse of a right triangle separates the hypotenuse so that the length of each leg of the triangle is the geometric mean of the length of the adjacent hypotenuse segment and the length of the hypotenuse. So we have a similar diagram below, and the proportion is C is to B as B is to X, and A equals the geometric mean of YC, and B equals the geometric mean of XC. Let us try one example where we can apply both theorems. We can use the geometric altitude theorem to find the length of the hypotenuse, which is y. So the lengths of the segment of the hypotenuse are 4 and 12. Therefore, y equals the geometric mean of 4 times 12. We will get y equals 2 because the square root of 4 is 2. And you could break up 12 into factors that are perfect squares. So you get times 4 times 3. And you will get y equals 2 times 2 radical 3. And you multiply whatever's outside the radical. So you get y equals 4 radical 3. We can apply the geometric leg theorem to find the length of the hypotenuse leg. So we add 4 and 12 to get the hypotenuse length of the big triangle, which is 16. And we plug that into the theorem. We also plug in 12 because it is the adjacent length. It is the length of the adjacent hypotenuse segment. So the proportion is 16 over x equals x over 12. We get x equals the geometric mean of 16 times 12. The square root of 16 is 4, and we break up 12 into 4 radical 4 times 3, and x equals 4 times 2 radical 3, and our final answer is x equals 8 radical 3. That is all for section 8.1, finding the geometric mean of two numbers. Any questions? Feel free to ask. Have a nice day.